Very well. Good morning, and welcome to Unit 7. We're going to talk for the next stretch of time, I think about 3 lectures, about optimization problems of different kinds in hybrid vehicles and mathematical optimization methods. So the basic structure of things, as you know, is that Monday there is a midterm. Wednesday we're going to have a second lecture on optimization problems. Friday we will finish the optimization section. And then from there we will start moving into the energy management and optimal control part again. And that will be the last unit for the class. There is a very slight change in the syllabus that I'm going to post for the OSU class. I already posted it for the distance learning class. We had to adjust a few dates to make sure that the lectures and the homework assignment due dates are consistent. And so there will be a slight update published, but for the time being, you don't have to worry about anything. Just focus on preparing for the midterm exam on Monday. So this is a generic picture. There is nothing particular about it, just intended to show you that there are many different architectures of hybrid electric vehicles that one could possibly imagine. They have to do with the type of vehicle, the type of duty cycle that the vehicle might encounter, your objectives. Is it going to be a plug-in? Is it going to be charge sustaining? And so this is just a series of pictures that shows you things going from SUVs to Formula One cars. So the question that you might ask yourselves is, how do I design an optimal configuration for a hybrid electric vehicle? What are the criteria? So you have a large problem in front of you. The large problem involves, first of all, input data. Input data is, first of all, what type of vehicle is this? Is it a delivery truck? Is it a 4-door passenger sedan? Is it a pickup truck? You know, you have many different possibilities. Not only that, but you typically would also want to have an idea of what type of driving this vehicle would do. For example, many years ago, I did a project funded by the U.S. Department of Energy with a company called Oshkosh Truck that has a division, McNeilus, that makes refuse hauling vehicles, in other words, garbage trucks. And we made a hybrid electric garbage truck. Well, what's the duty cycle of a garbage truck? How is it driven? Very simple. It's driven like a Formula One car. The driver accelerates like crazy from one stop to the next, then brakes really hard, tries to load the garbage as fast as possible, and then accelerates really hard again. So it's a little bit like a Formula One car going into corners and coming out of corners. Okay. On the other hand, if you're doing something for an all-purpose passenger car, you have to take into account the possibility that you might be driving in urban traffic that is very dense, on a freeway, and anything in between. So the next thing you're going to take a look at are constraints. So we've looked at the fact that you have a set of input data. Input data is basically what vehicle it is, what kind of duty cycle it has. Next, you have constraints. The constraints are going to be, here is a picture of a truck going up a hill. If you don't have enough torque to be able to start on a certain grade, for example, that would be a problem, right? So you're going to have some minimum torque from 0 speed that you need to be able to to provide. You may have other constraints that have to do with the mass, the weight of the vehicle. You may have the biggest engine you can get is a 200 kilowatt engine, and so on. So you're going to have practical constraints. Then you're going to say, okay, I'm going to do some kind of an optimization of this and compare different types of architectures, which is exactly what I'm going to talk to you about today. And so the question is, how are you going to optimize this? You know, everyone learns in calculus, some of you did it in high school, that if you want to find the minimum or the maximum of a function, you calculate the derivative, set it equal to 0, and that's going to give you the minimum or the maximum. Fine. Those type of things, if you extend them to more complicated system, instead of calculating derivatives, if they are multidimensional, you will calculate a gradient, which is a multidimensional derivative. That's one way of doing it. Another possibility is you could do an exhaustive search. I'll give you an example of that. You're going to say, all right, I'm going to build 1,001 different vehicles with different configurations, different architectures, and I'll simulate all of them, and I'll see which one gives me the best answers. Or you could come up with other optimization methods that are what we call derivative-free optimization. So they're not exhaustive searches. They do use an algorithm to find the minimum or the maximum, but they do not use derivative. For example, the Nelder-Mead simplex algorithm is an example of one such thing. Some of you may have heard of things like genetic algorithms, for example. Those are also derivative-free optimization algorithms. But when you optimize something, you're going to have to decide with respect to what. You come to me and I say, I want the best vehicle you can design. And I'm going to then ask you, well, best with respect to what? And you say, minimum fuel consumption. That sounds fair, right? So then I'll tell you, okay, fine, here's a fantastic design. This vehicle will cost the customer $1 million. Obviously, you forgot to tell me that you want the best fuel economy, but you also want it to be affordable, okay? Fine, so we make the best fuel economy that is possible, and we make a vehicle that costs $30,000. We're good, okay? Then I go on the test track and drive it, and this vehicle drives like a dog, okay? No acceleration whatsoever. Why? Because I only privilege fuel economy. What about performance? So you can see that I could add to fuel economy, cost, performance. How about packaging and mass? Is it possible to put all the components you want in the space that is available in the vehicle, et cetera, et cetera? There are many, many different examples. So you have to define a cost function. And the cost function could be CO2 emissions, dollars, packaging. There are many ways, and some of these cost function elements could be defined mathematically. Some others are more subjective. Packaging, for example, that's not so easy to write an algorithm that says this package will fit or it will not fit. So the idea of how to define a cost function and how to evaluate all of these choices that you have is actually a fairly complex problem. The overall problem of putting all of these things together is called the design space, and what we want to do is a design space optimization where we're going to have to optimize the topology or architecture, series hybrid, parallel hybrid, one motor, two motors, planetary gear sets, manual transmission, many different choices. Then you have to optimize the relative size of things. So let's imagine that you decide that you want a P2 configuration. Great, P2 is fine. Now, how much power from the engine, how much power from the electric motor? What size should the battery have? And finally, and this is really important, okay, you're going to have to do some energy management. You can have an architecture that is fantastic, but if you have a poor energy management strategy, you will not come close to obtaining the best possible outcome you could have. So in this loop of what's the best architecture, what's the best size of components, and what's the best energy management strategy, you can imagine that you could be doing lots of iterations and that it's not easy to come to a final solution. If you forget about the energy management strategy, you really haven't optimized. Okay. So in summary, what we're saying is that you will have to specify input data such as the target driving conditions. You're going to have to specify constraints, for example, maximum component sizes, maximum budget, okay? you're going to have to identify the optimization targets, that is, the cost function. And cost is intended here in the sense of an optimization problem, not just cost in dollars. So you would have fuel economy, performance, and then cost in dollars as well. And finally, you're going to have to decide, how am I going to search? What algorithms am I going to use to do this? So that is the introduction to the subject we're going to cover today. Then, in the next two lectures, we're going to talk about the beginning of how you would approach an optimization problem. So I'll teach you a little bit of the mathematics behind optimization strategies. By the way, we talk about this in the context of hybrid electric vehicles, but in engineering, every design problem is like this. The cost functions are different, the product is different, but fundamentally, you always have to face a trade-off between something and something else, and maybe something else yet. So all engineering is about optimization. So let's talk about the problem definition. So here is a diagram that Claudia very kindly created for me, extracting it from a few slides that had too many words. This makes it a lot easier to follow. So you have to identify optimization criteria. They need to be quantifiable. So for example, minimum fuel, that's quantifiable, okay? Sometimes there are criteria that are harder to quantify. They are, let me call them soft criteria. You know, minimum fuel consumption, well, you can measure that. So many grams of fuel over a driving cycle. But performance, well, you can say 0 to 60 acceleration, maybe, but there are drive quality issues. There are other things that may not be as easy to quantify. So when you have defined what your optimization criteria are going to do, you can then say, all right, let me write an objective function, and I'm going to show you examples very soon, and I will take into account all of the criteria I want. And then I say, okay, in my design, how important is fuel economy? Oh, that's really important. Okay, I'll give it 50% of the weight. How important is performance? Oh, that's pretty important too. I'll give it 25% of the weight. And don't forget cost, I'll give that the other 25% of the weight. Then you go talk to your chief engineer, and the chief engineer says, no, cost is 50%, right? So, sorry, this word should be weighted. So you create a weighted sum of these things where you say 0.5 times criterion 1, 0.25 times criterion 2, 0.25 times criterion 3. Now, the problem with this approach is that you can solve the problem, then tomorrow you wake up and you say, well, I didn't really want 0.5, I wanted 0.4. You're going to have another answer. So the problem with this weighted sum is that every time you change the weights, you change the optimization problem. So is there an alternative to doing this? Well, we could take a different pathway, and we could take an approach in which we're not going to make an a priori judgment. And I'm about to show you an example that illustrates that approach in a few minutes, okay? You don't make an a priori judgment, okay? You just simply do not formulate a single objective function. You say, these are my costs. Let me simply calculate what these costs are, and then I can compare them to one another. I can do a big search, okay? I can come up, I will show this to you literally in 2 minutes. You can do a big search and calculate all the possible answers, and then you say, okay, let me compare in some fashion these answers to see which ones I like better. Okay. This process here, instead of algorithmically giving you a single answer, here is my minimum, it's going to cause you, the designer, to have to make some choices among trade-offs. So what are some of the characteristics of these optimization problems that make them interesting and challenging? Well, first of all, you typically have a very large number of design variables. You can select the gear ratios in the gearbox, the size of the battery, the size of the electric machine, the size of the engine, and I'm not even going into architecture. Then you're going to have to assess the objective function. You're going to have to say, okay, here is a design. How does it do? Well, I'm going to have to simulate it over a drive cycle, right? I'm going to have to say, okay, I came up with a design. Let's drive it over an urban driving cycle, a highway driving cycle, a mountain driving cycle, and let's see how it does. And I have to do this with a controller. So for every architecture that I have selected, I have to have a controller that is good for that architecture. I can't just put in some random controller because, as I said before, if the controller doesn't do the right job, then you will not know how good your architecture is. And the design variables and the control parameters are very strongly coupled. So that means that when you put all these things together, you have a large-scale numerical problem. Now, we're engineers, and we know a lot of practical things, I hope. So expert knowledge may help us bound and reduce the problem. So, for example, I am General Motors, and I know that at GM I produce so many engines. So I have a 2-liter turbocharged gasoline direct injection engine that produces, give or take, about 200 kilowatts. I have a 2.4-liter naturally aspirated engine. I have a 3.5-liter V6. So I don't have an infinite choice of engines in the design. So I'm going to bound myself to say, let me pick these 4 or 5 possible configurations. Why? Because I know that I have them already. And there are other practical constraints that you can impose. You also should pay attention, and this is really important, about the sensitivity of the solution. For example, one of the criteria that you typically end up optimizing in the design of every vehicle, even if it's a conventional vehicle, is the final drive ratio. You know, you are going to connect some kind of a transmission output shaft through a differential gear set to the half shafts that go to the wheels. Well, the choice of that single gear ratio actually has a very, very strong impact on the fuel economy of the vehicle. Many, many years ago, when I was your age or younger, Renault had come up with a version of a vehicle that was very popular in those days, the Renault 5. Renault 5, which was sold in the US for a period of time. They call it Lecture here. Anyways, there was a version of that vehicle that was designed for fuel economy, and all it had was a really long final drive ratio, which meant that on the freeway, you actually were able to get the RPM down quite a bit. So you had very good fuel economy. The problem was that if you were trying to go 120 kilometers an hour and the freeway went uphill, in those days, by the way, the gearbox had 4 speeds, you couldn't do it in 4th gear, kind of like your car, Leela. You had to downshift, okay? Why? Because with that really long final drive ratio, you didn't have enough torque. Okay. So my point is that even just something as simple as selecting the final drive ratio, it interacts with a lot of things. And so everything is complex. So a summary of the steps that we're going to follow: define the optimization criteria, typically many. Define the relative importance if you're going to do a weighted sum of these criteria. Identify constraints. Some of these constraints, by the way, are really tough, like you have to meet emissions. How do you write that in an equation, in an optimization problem? Wow, that's really complicated, right? You're going to have to decide the powertrain layout, okay, the architecture of the vehicle, the sizing of the specific components, what control policy or energy management strategy you're going to use. For example, you say, oh, I will use ECMS for every one of these architectures, but then you're going to have to calibrate this ECMS for every different architecture. What's the evaluation tool that you're going to use? Well, in our world, we're going to use some kind of a simulator which hopefully has been validated. In other words, I've gone out on the road and validated that at least for the conventional vehicle that my simulator is working. Then we have posed an optimization problem and we need to solve it. When we've solved it, we say, I found the minimum. You're not finished. Because now you have to test the robustness of the solution. Because you might say, oh, my supplier just told me that my gearbox, I ordered a 6-speed automatic transmission, but they don't have the speed ratio I wanted. They're slightly different. Is my solution very sensitive to the individual speed ratios in the gearbox? I have to find out how robust the solution is. So, overall, today we're going to pose the problems, or the questions of how do we formulate a problem like this practically, what tools do we have and how do we use them, and how good are our solutions. And today's lecture, it's a good lecture for a Friday. It's kind of relaxed. I'm going to tell you two stories. One that is based on work that we did in 1997, believe it or not. And the other one is based on work that we did in 2019. So what has happened over 22 years? Actually, I'm joking, not much, in the sense that the mindset and the approaches that we follow are still the same, but computers are a lot more powerful. So that's a good thing. Okay. So many years ago, I worked with a group of people who were in the computer science and engineering department here at Ohio State in a laboratory for artificial intelligence research. And they had a project supported by DARPA to develop software technology for exploring large design spaces. DARPA is the Defense Advanced Research Projects Agency. And this was a general methodology study. They wanted to support some research in a methodology study. So my friend, Professor Chandrasekaran, came to me and said, hey, we need an example for a large design space search. Well, at that time, we were working on the Future Car project. Future Car is the great-great-grandfather of EcoCar. And we had just gone through the process of trying to select an architecture for the first phase of this competition. We had a 4-door family sedan. It was a Chevrolet Lumina. It doesn't exist anymore. Today, the comparable vehicle would be the Chevy Malibu. Okay? And what we needed to do is design a hybrid electric vehicle. We had done a phase 1 of the project, 96, 97. We were going to modify this design for the 98, 99 competition. And so this was a good time. I said, I have an example. Let's explore the design space of hybrid electric family sedans. And one other comment, this is actually historically very important. Brian Wozak, who was a graduate student then, who is now an executive with FCA responsible for powertrain control and electrified powertrains at FCA. He was doing his master's thesis. He was the first author of a hybrid electric vehicle simulation. That was his thesis, okay, back then. So we felt good. We had a Simulink simulator that simulated a hybrid electric vehicle. So we said, okay, we have this thing. So what did we do? So what are the characteristics in this? So this particular approach was an AI, artificial intelligence, computer science-oriented thing. And their idea was that instead of trying to algorithmically improve incrementally some designs, let's say that we create a huge design space and we let computers automatically generate and evaluate designs. So we're not going to limit ourselves. We will do a brute force search. So what happens, however, is you know that if you randomly generate all possible combinations of designs, some of them are going to be pretty dumb. They really will not work, okay? The engine and the electric machine, for example, could both be too small and the vehicle will never have the performance you want. Now, an engineer would know that, but the approach that they wanted to select here was to say, no, 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 let us create everything, because there might be some hidden nugget, a gem somewhere, a diamond in the rough that we didn't know was there, and we might not have thought about. So let's look at all the possible combinations. But then we create some kind of a filtering process so that we eliminate also automatically the backgrounds. Now, when you're done with this, as you will see, you will come up with still a large number of choices. You will be surprised by the numbers I'm going to show you. Remember, 1997, okay? And then these people were computer scientists. They were very good at coding stuff. So they said, we'll make an interactive graphical interface so that the human engineer with experience will then go and compare things and pick the best ones. Okay. So early design process. This is a potentially good architecture. And the software has a seeker, which generates a gazillion options, a filter, which reduces the option to a smaller number, and a viewer that allows you to see what you've done and then select from there. So what's the seeker? Well, basically, you have a library of devices and configurations in various alternative forms with some representative parameter values. For example, 2-liter turbocharged engine, 2.4-liter naturally aspirated, et cetera, et cetera. Then you evaluate the design according to multiple criteria using simulation. And you're not going to say, oh, acceleration counts for 20%, fuel economy counts for 80%. No. You're just simply going to evaluate these criteria. So at the end, you're going to have so many different outputs, okay? No judgment made yet. It's a big search, right? Because we are not limiting ourselves. And this search could be massive, and we would like it to be exhaustive. We would like to make sure that at the cost of simulating some pretty stupid architectures, we will, however, not miss some hidden treasure that we might not have found otherwise. The largest experiment we did at that time was over 2 million designs. If you think about it, that's a pretty big number today, okay? And of these 2 million designs, about 1.8 million were actually doable, fully specified. Some of the things that you could create would not run. I mean, I'm not going to go into the details of why, but accept the fact that we had about 1.8 million designs that we actually could simulate and specify. And each fully specified design for this hybrid electric, it was a parallel or series hybrid Lumina, they were all then exercised using multiple simulations. Why multiple simulations? Well, I'm interested in things like acceleration, top speed, city fuel economy, highway fuel economy, and for each of these things, I'm doing a different simulation. How was the search done? This is the part that was really cool. At that time, the computer science and engineering department had 209 workstations. We searched the entire design space in 6.8 days. That is a pretty good time today as well. How did they do it? They helped us convert. Well, we did the conversion. We converted the Simulink models into S functions, C code. They then embedded the C code as parasitic processes, okay, almost like a virus, okay, in the background, so that whenever a workstation was idle, it would run one of our simulations, okay. And they're computer science people. They knew how to do this stuff. So the idea is that in the downtime, without disturbing, this would be the lowest priority job on these 209 workstations. For example, at 3 in the morning, sometimes even computer science students go to sleep. It's possible, I mean. So the idea is that the maximum number that ever ran at one time was 159, probably in the middle of the night. It's pretty good. Actually, maybe not 3 a.m. I think computer science students sleep at 9 a.m. I think it's different. So that was fine. So we created a super large set now of results, because for every simulation, we have so many different instances of driving cycles. So now, we suggested the idea of a dominance filter that would greatly reduce our output space. What's a dominance filter? The dominance filter says the following. If I have a design candidate A, and in every performance index, this design candidate A is better than design candidate B, then why would you keep B? It doesn't accelerate as well. The fuel economy is not as good. Why would you want that car, right? So we looked for designs that completely dominated the other ones, okay? If, on the other hand, and so dominated designs, those that are clearly inferior in every criterion, are removed. And, of course, the surviving designs are Pareto optimal. Pareto optimality, if you have never heard of that expression, is a concept by which you may have two cost function criteria. J1 is one cost, J2 is another cost, okay? Before I explain Pareto optimality, I just remembered that I wanted to say happy Halloween to everyone. I'm sorry about the distance learning student. I can't give you candy, but if you want to pass this around. With all the wind and cold that there was last night, we had very few trick-or-treaters, and there was a lot of leftover candy this morning. I thought it was better to distribute it to the class than to eat it myself. Okay. So I have two costs, J1 and J2. For example, J1 could be acceleration, and J2 could be fuel economy. And I come up with a lot of solutions. So I'm going to have a whole bunch of different solutions. So because every design has a certain value of J1, and any other design has a certain value of J2. What's the best value? So better is closer to 0. I am minimizing, okay? So the ideal vehicle is one that takes 0 seconds to go from 0 to 60 miles per hour, consuming 0 miles per gallon. I'm consuming 0 grams of fuel. Okay, that's the perfect vehicle. Of course, it's impossible. So when you look at this, what do you find? What you'll find is that there is going to be a region where, in this case, these are dominated designs, because you can find designs that are going to be better than them. I want to erase one point here. There you go. On the other hand, if I look at these points here, these create what we call a Pareto curve or Pareto front. What does that mean? That if I choose the design, I'll make it green because it's the best fuel economy. The design that is going to have the best fuel economy is this. But it also has the worst acceleration, biggest time from 0 to 60. On the other hand, I'm going to go to the opposite direction, find this design. This has the lowest value of criterion J1, but the highest value of criterion J2. So what you have here is a trade-off. Anywhere along this line, you're going to have something where if you move in one direction, one criterion gets better. If you move in the other direction, the other criterion gets better. It's a trade-off. That's the choice you're going to make. Now, when you make comparisons, we're going to specify some tolerances. We're not going to make the mistake that many students make. MATLAB, one of the biggest flaws of MATLAB is by default it gives you 4 decimal places. So I get answers in homework assignments that look like 179.52735. Okay. Do you really think that the last 4 digits mean anything? Okay, they don't. So in specifying, is this design better than that, we're not going to go to the 4th decimal place, okay? So we're going to create some tolerances. That's important. And The tolerances are very important because they essentially interpret knowledge, meta-knowledge, higher level knowledge that we have about the accuracy of the simulation. I mean, if you were doing an atomistic simulation where you got a bunch of quantum physicists to model the hybrid electric vehicle for you, then maybe that fourth decimal place is important, maybe, okay? But it would also take infinity to simulate it, okay? So we have some idea of what approximations we have in our model. So for example, if I'm comparing fuel economy, honestly, to me at 32.5 and 32.3 miles per gallon, I know that my simulation is not that good. They're the same number for practical purposes, okay? So dominance filtering can be very effective. So we did an experiment. We used 4 criteria and some simulation model, actually the ones that we used later in the big study. And we looked at a certain number of designs. We started with 1,800, then we went to 18,000, 180,000, and 1.8 million. So by factor of 10. And this is the number of survivors that you have. How many elements do you have in that Pareto trend? Okay? And look, with a small number, some 4% survived. By the time I looked at 1.8 million, only 0.06% survived. So this filtering, when you're doing very large-scale brute force searches, is a good and effective. Okay? So next, not only that, but it scales well, which is a good thing. It's important. We don't want to, if you start with 2 million designs, and by the time you're finished with this process, you have 200,000 designs left, that would be difficult to manage. Then, the next step is, let's view the trade-offs. Let's now bring the human into the loop. And that was the project for which Professor Chandrasekaran was funded by DARPA, was about inserting the human in the loop of AI-based design optimization techniques. And so there is now an interactive viewer. You want to actually see these trade-offs, visualize them, compare them multidimensionally because you have multiple optimization criteria. And can you zoom in and take a look at the details of this? Can you select subsets? And I'll show you how the graphical viewer appears. So here is an example in which you have each X, and you don't see all the X's because some of them are on top of one another, but you have a graph with 1.8 million X's, okay? And what's this? This is highway fuel economy, and this is city fuel economy. Numbers are miles per gallon. Lower is better. Well, are you surprised that there is a strong correlation between city and highway fuel economy? No, you should not be surprised. That there is a spread is pretty clear, but it makes sense that they should be correlated. You say, I know my answer. I'll take these. That's the best highway and city fuel economy. I can get 85 miles per gallon on the highway and 60 miles per gallon on the city. By the way, that was 1997. Those are pretty good numbers today, right? Okay, all right. So, but we only compare 2 criteria. Wait a minute, we're not done. Now, I say, wait a second, I had other criteria. So what I have is highway, okay? I'll call that H. And so here I have H on the horizontal axis, here I have H on the vertical axis. Then I have another one that I'm going to call city. That'll be green, and I'll call it C. So city, 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 and then that's it. Then I have something else that I'm going to do in black that I'm going to call acceleration, A, okay? And acceleration would be time to 60 miles per hour. Oops, black doesn't work very well. A, acceleration, A, acceleration, A, acceleration, and A, acceleration. So that's time to 60 miles per hour, okay? And finally, the last one that I'll put in red is going to be the top speed. Because we said, hey, look, this vehicle has to have some acceptable top speed, right? You could have great fuel economy, but if your top speed is 45 miles per hour, you probably won't market that vehicle very well. So we have S. There should be another one. No, I guess that's what I have. Okay. So now that I have considered all of these things, I can see that there are some criteria that, this is the first graph I already showed you, that correlation is obvious. Here, the correlation is less obvious. There are kind of like three families of things that happen. Here, you have a negative slope if you were to do a curve fit. So there are different things, different relationships among these criteria. So if I only chose the best up here, which have the lowest fuel economy, they may not be the best in terms of performance, for example. In fact, they will not be. So let's take a look next. I could then say, well, I know that if I am going to sell a family sedan, I have to guarantee to my customers that the time to 60 miles per hour, the time 0 to 60, should be acceptable. So we arbitrarily, the numbers are not so important. We just wanted to illustrate a point. We said, look, no one will buy this car unless we have a time that is better than 12 seconds, lower than 12 seconds 0 to 60, okay? So that means now that I have eliminated lots of designs, because now I have imposed a constraint that says this is, I have to do at least that, okay? Those fuchsia colored, so the red ones I've eliminated, the fuchsia colored I've kept. Now, this graphical user interface allows me to see graphically in those same 6 planes that I showed you before, which ones the good ones are. And I want to go back now to the very first plot. The very first plot I showed you was this, and I said, oh, the best fuel economy is up here. But you should not be surprised to know that the vehicles that get that really good fuel economy will not have the performance that we expect. So if we had blindly gone only on fuel economy, we would have failed because the vehicle would have been not customer ready, okay? So not only that, but you may notice that this is an interesting point. You will notice that you have similar designs that are close to one another. Some of them are good, some of them are not. So you can arrive at similar fuel economy with designs that give you good performance and with designs that don't give you good performance. So learning what the difference is between these two little clusters, going inside and seeing what the components are, may teach you something. Maybe it was something that was already obvious, maybe not. Is the difference all in the transmission and final drive ratio? Is in the size of the engine, in the size of the battery? Those are things that you have to ask. So that is a very good criterion to link the displays. And so now, in the next step, those that were red and we said they're not good enough from acceleration perspective, I'm eliminating them. So now I have narrowed the set. And all of this you can do in this software by circling things with a mouse and drawing a line, and it will select it for you. So that's what's left. What do you do after you've narrowed the sets? Well, let's take a look at them again. So now I'm going to pick another criterion. I'm going to want to look at top speed. Again, another arbitrary number, but we said, look, if this vehicle cannot do 85 miles per hour top speed, it really cannot compare to a production vehicle. That's a reasonable number. So we draw another line. And so there is, interestingly, a subset of vehicle that will give you the acceleration you want. It'll do that fine, but it won't be able to top out. Some of these, the top speed is only like 65 miles per hour. That would not be safe, actually. Plus, if you have a hill, it's even worse. So, by the way, what do you think is the cause of that? I say gearing. I think this is all transmission and final drive related. That is, the gearing is short, so it'll give you good acceleration, but it won't give you top speed. So we eliminated poor gearing choices. Now, I have eliminated anything that does not have sufficient acceleration and does not have sufficient top speed. I have now guaranteed that I have some criteria of performance that are acceptable. So I further reduced the set. This is a much smaller number now. Now I can take a look at it and say, let's go back to fuel economy. That original highway fuel consumption versus city fuel consumption. Let's now go see what's the best. And it's clear that there is a cluster up here that is the best in class. Okay, so those are, and you know, the other thing that I say, this is a simulation. I don't take the numbers too literally. So the difference between 70 and 60, yeah, my simulation is not that good. So I'll keep all of these, okay? And now that I have selected this subgroup, I can further go into additional selection and decide what I want. For example, I may want to privilege city efficiency. I want to look at those numbers because I think that it's very important to improve the city fuel economy more than it is to improve the highway fuel economy. And in the end, after doing an interactive selection process with some engineering experience in it, I end up with 7 alternatives. Now, this is an interesting question at this point because you say, okay, if I believe my simulations, you know, to a reasonable extent, I now have 7 designs. Who wins? Are they all P2? Could some of those be different? Could they be series hybrid? And so at this point, you would go inside each of those designs and understand what are the architectures that give you the best solution. And it turns out that those 7 architectures are not slight variations on a theme. It turns out that there were actually multiple architectures involved in that. Then at that point, you have to think about, okay, if I now were to bring in cost and complexity, given that the 7 architectures give me similar numbers, which one might I be able to produce at a lower cost or with greater reliability or with less complexity, et cetera. This was a very early study, and it was really a demonstration. I wouldn't use this study to, you know, start a product, okay, to launch a product. But you can now look at all the different trade-offs, and with the human in the loop, we have the ability to make decisions that in which we don't force at the beginning a weight on each cost element of the cost function. We leave everything open, and in interacting with the human, the system allows us to come up with a Pareto solution. Now, more on the viewer. You can also link the scatter plots to a bar chart. So, for example, you could say, when I look at fuel economy, what's best? Well, you can say that this is a silly, you knew this already, but this illustrates that if the engine can be small, medium, or large, all the better solutions involve small or medium-sized engines. Downsizing is a good idea. We knew that already, okay? But this is shows you. Then it's going to say, okay, of the ones that have a good trade-off between city fuel economy and time from 0 to 60 miles per hour, how many of those actually utilize a small engine? And if you look at 1,078, okay, before we do the final narrowing down, how do they spread out? Well, this is the range of values of top speed, highway, highway range was another criterion. On a full tank, how many miles do you get? Right? Vehicle type, look at this. There was parallel charge sustaining, parallel charge depleting, for example. Weight, this is the distribution of weights that you get from the possible configurations. Notice that this has a powertrain weight of 968 pounds. This is 580 pounds. The range is substantial, right? And you can link all of these criteria. By selecting a subset, you can display where those answers, in our case, we have things like gears, rear axle ratio, battery size, etc., etc. You can link all of those and see where your best solution fall from a design perspective. So this is just a little bit of good programming. You could link many different types. So the viewer allowed us to compare things and also go a little bit deeper to understand what are the elements of a good design. And so the notion is that as you do this, if your simulation and your performance criteria are well selected, you may learn quite a bit in the process. In some ways, this was a very naive exercise because the simulator was very simple. The criteria that we selected were also very simple, but it was a very good exercise for us to explore different solutions. Years later, Claudia's advisor came to visit me, and she helped us develop improve these methodologies. I think we used genetic algorithms way back when. And so a few years later, we published another paper in which we had done some slightly different things. But over the years, we have done many studies like these. There was a period of time when we worked with the U.S. Army Tank Automotive Research Development and Engineering Center to take a look at medium-duty tactical trucks. If you had electrified powertrains in medium-duty tactical trucks, how would you optimize their design? We took a look at off-road vehicles. So we did a variety of things over the years. Most recently, we have worked on a project funded by the U.S. Department of Energy in collaboration with Cummins, Freightliner Custom Chassis, and other partners, in which we're taking a look at a very important type of vehicle, very important today. This is a typical delivery van, also called package van. And what I'm referring to is the UPS, DHL, FedEx, Amazon, you name it. We see these package vans on the road all the time. They have replaced shopping in the store for many people. And tomorrow, it will be reasonable to expect that in cities, in urban areas, you would want these vehicles to have very low emissions. So maybe we should think of them as electric or hybrid vehicles. And the architecture that was selected for this project, which is currently being done, this is a project that we're doing now, is an extended range electric vehicle, sometimes abbreviated EREV. What does it mean, extended range electric vehicle? Well, it's an electric vehicle because ideally you would like to have an electric vehicle when you are delivering packages in the city, because locally you have zero emissions. And in densely populated urban areas, local zero emissions, even though somewhere else, yes, there may be emissions from a power plant, but locally it's a good idea to keep the urban area clean. So now, what are the possibilities that we have? Well, I am showing you 4 conceptual architectures. There are many ways you could do this. One of them is based on this idea. First of all, let's start with the simple one. I have a conventional vehicle with an engine and a transmission. Typically rear-wheel drive, if you've ever seen this package van, they're big boxes. Next, you say, oh, I'm going to make it electric. So what I'm going to do is select an electric drive, and it's a direct drive. The only gear I have is a differential. I have a final drive reduction. That's the only thing I have. And of course, I'm going to have an internal combustion engine, and the internal combustion engine serves only the purpose of generating electricity so that it can supplement the battery if needed. It's a series hybrid, right? And you say, well, do I have to do a direct drive? I could take advantage of a transmission of some kind so that I may be able to make my motor smaller because I can multiply its torque by way of an appropriately selected transmission. And by having a multi-speed transmission, my performance will be better. At 0 speed, I can be in first gear, have better acceleration. If I need to go on the highway for a stretch of time, I'll go to a higher gear. There is a reason for transmissions, right? And I still have the same genset here. That part hasn't changed, but now I have to decide 2, 3, 4 speed, okay? And where is the electric machine? We took a look at solutions that are called e-axles, where the electric machine is actually integrated in the rear axle of the vehicle. Remember, these are big trucks. There's a little more room under the floor of the van. Finally, the last configuration that you could consider is a dual motor. And I could say I still can go to a direct drive, but now I'm going to have 2 electric machines. And you say, why would you do that? You already could do it with 1 electric machine. But if I am driving at relatively low loads and speed, a single larger electric machine will probably operate in a relatively low efficiency region. If I have 2 smaller electric machines, I can use one or the other. Maybe I alternate between the two when I'm at low speed, low load, because the smaller machine will operate at a higher efficiency point. So I could, in principle, have better efficiency overall if I have 2 electric machines. And when I need more power because I'm driving 60 miles per hour on a highway, I use both of them. So there are components that I need to select. What are these components? They're engines, electric machines. By the way, there are so many different things you can choose from, right? So for example, do you need a torque converter in the transmission? Maybe, maybe not. Okay? Is your transmission a stepped automatic transmission, or maybe that uses clutches and the like, so planetary gears, or could it be a lay shaft transmission with 2 or 3 speeds, kind of like a manual transmission, maybe automated? So that's the option of the transmission. That's a lay shaft transmission here. And of course, you have a trade-off, right? You can always have a smaller battery and a larger generator set, or a smaller generator set and a larger battery. At the end of the day, you'll have to decide how much energy. These vehicles are plugged in. There's no question about it. But at the end of the day, how much of the energy should come from the fuel and how much from me plugging into the electric power supply. Of course, I'm going to have to come up with an energy management controller, okay? And finally, I'll consume the energy, I'll calculate the energy consumption. And by the way, the energy consumption, in this case, I have to be careful how I evaluate it because there will be fuel for the engine, but at the end of the day, I have to plug in, so there is a cost to the electricity and eventually a CO2 emissions cost. So we created a configuration that is a general configuration. This is not to be taken literally. So we're going to have a genset, a battery, 1 or more electric machines, maybe, maybe not a transmission, and if there is one, it could be 2, 3, 4 speeds, okay? And so we created a simulator. And what has changed between 1997 and 2019? Well, one of the things that has changed is that our simulator is much, much more sophisticated, much more, much closer to the reality of what the vehicle does. And a lot of the simulator development, it involved a year of work with Cummins and Freightliner custom chassis to validate it against experimental data. In fact, we did experiments on the heavy-duty chassis dynamometer at CAR to actually create a database for the conventional vehicle so that we could validate our conventional vehicle simulator against data collected from the conventional vehicle. So this design space exploration did not use a brute force search like the 2 million cases. We could have done that as well. And by the way, today we might have done it even faster, right? Because computational power is much greater. But what we did was to embed in our design space exploration a lot of prior knowledge that came to us from our industry partners. They said, guys, you can argue all you want about what the engine size should be and give us the optimum, but in reality, we're going to be able to give you engine A, engine B, and engine C. That's what we've got, okay? So don't bother optimizing too much. You have 3 choices. That's just an example. Don't take that too literally. But the point is that a lot of practical engineering went into the design space exploration, including, by the way, what are components that are available? Because this project will eventually lead to the demonstration of a real prototype, complete, fully functional. Okay? So I can't say, oh, wouldn't it be nice if we had a 19-phase permanent magnet electric machine where the permanent magnets are made of unobtainium and I have amazing efficiency of 99%. Well, that machine doesn't exist, so there is no point in putting it in the simulation. So again, we had to look at what was possible. So we understood that things like the motor continuous power range would be in the 150 to 200 kilowatts. The first gear ratio would be about, if you have a transmission, would be about between 1.5 and 3. Final drive ratio was already selected. So there were some practical design criteria that were fixed. So what's the problem from an optimization standpoint? We had to construct an objective function. We want to minimize over the inputs, the cost, okay, over a driving cycle. This cost includes the obvious thing, fuel consumption. That's the same thing that we've talked about so far, minimizing the integral of m dot sub f. But we then had to think carefully about 2 other criteria. These are functions that incorporate the genset start penalty. If you do not assign a cost to starting the generator set, every time you start the engine, there is going to be some extra additional fuel consumption for the engine start. So we said, look, every time you start that engine, you're going to consume an additional 10 grams of fuel. If you made it, there are also emissions penalties, but in this particular study, at the beginning, we are considering emissions as well, but in this study that I'm showing you, we did not. We had not yet done that. So if you did not put a penalty on the engine start, the optimal solution might be continuously starting and stopping that engine. And in practice, that's not a thing. Second, if you have gears, okay, every time you're doing a gear shift, stuff happens. You have clutches going in and out. There are things that go on. So we also penalized in some way gear shifts. Now you say, how do you penalize a gear shift by a gram of fuel? Well, that is more of a tuning parameter. We want to have the same units, right? So we assigned it a cost in fuel. In fact, gear shifting is more of a drive quality issue. It will affect the fuel economy as well. So anyways, we tried to make a cost function in which we considered fuel economy, engine start-stops, and gear shifts. Now, this makes the problem interesting because what are the state variables now? Well, one state variable is the obvious one, the state of charge. We talked about it in describing the equivalent consumption minimization strategy. That's obvious. But we now have 2 other variables that are different. SGen, the state of the generator. Ooh, this is binary. On or off. Okay, so now I have a continuous variable and a discrete variable that can take on values only of 0 and 1. Further, the current gear, the state of the gear, okay, that's also discrete. Now, it's not necessarily binary because I could have first, second, third gear, fourth gear. I mean, it could be, but it's discrete, okay? Those are the state variables in this problem. What are the control variables, U? Well, U is the command you give to the generator, meaning on-off switch. So U-gen is 1 or 0. Is my engine on or off? Do I turn it on? Then I have P-gen. I have to decide how much power to make with the generator set. And I also have a way of controlling the gear setting. So that's also, so 2 of these inputs are discrete and 1 is continuous. Now the generator set power automatically tells you how much power you're going to get from the battery, right? Because you have to satisfy the power request of the driver, and that's the sum of 2 things: generator power, battery power. What happens if the engine command is off, the generator command is 0? Fine, all the power will come from the battery. That's easy. So I have a combination of states and inputs that can be continuous or discrete. And there's 2 letters that are very important. They will appear in the homework assignment and in the final exam. DP, dynamic programming. Dynamic programming is a particular optimization approach that I use for solving optimal control problem, and I will lecture in detail. You will do homework assignments. So what I did now is I just formulated an optimization problem that I will solve algorithmically. Here is my problem. I want to minimize a cost function J. I define the cost function J. Here are my state variables. 1 is continuous, 2 are discrete. And here are my inputs. 1 is continuous and 2 are discrete. That's my optimization problem. Then I feed it to a hungry beast called dynamic programming that is going to eat up all of these things and spit a solution. So I have a variety of objectives, because when I calculate this solution, I then have to decide what are the objectives that I have. And so, for example, cycle fuel consumption is 1, but I might want to take into account weight of the powertrain. In a commercial vehicle, if I make the powertrain heavier, my payload becomes lighter. I have less cargo that I can carry. So here is an example in which I show you some of these results. This is, again, a design space simulation, but here I'm not talking about 2 million cases. I selected a certain number of battery sizes, a certain number of options for the transmission gear ratios. There are many choices, okay? And careful, I have some performance criteria. I have to be able to, for example, one performance criterion is grade. You have to be able to go up a grade at a certain speed with a certain % grade. So they call it grade at speed, okay? You have to be able to have a top speed. You have to be able to have a certain acceleration. So we did all these simulations, and so in that sense, we're back into the simulate, 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 brute force kind of search. And we have 2 cases. Blue means that all my performance criteria were met. This vehicle would perform like your basic UPS truck that you see on the road today. All the criteria, and how do we know that? Because our partner, Freightliner Custom Chassis, together with Cummins, make chassis and powertrains, which then they sell to UPS. So when you see the brown UPS truck, many of them, I visited, by the way, the factory, very interesting thing. When you see a brown UPS truck, I know exactly what's in it, okay? So we wanted to match that performance, and so blue is okay. Red is a fail, okay? Red means you can't go 30 miles per hour on a 30% grade, for example. Okay. So now you can see that the blue ones are all acceptable. But what do we want? We have fuel consumption. In this case, fuel consumption is the total weight of the fuel, mass of the fuel used. So it's grams. So lower is better. And motor size is, what's the motor size that you need? Well, maybe smaller is better here too, right? Smaller machine presumably is like. So you can see that here we have created something that is like a Pareto front of possible solution. So in some ways, the end outcome of this simulation is very similar to the 1997 work we did, but it's much more sophisticated in the models we used and in how we solved the minimum fuel consumption problem through the use of dynamic programming. So here is another example. This is fuel consumption versus motor size, grade, feasible grade. So this is the case in which we looked at the 3-speed automated manual transmission plus electric machine optimization. For this one, this was a case where if you now are looking at the 3-speed case, look at that. You don't really have a Pareto front. In that particular plot, there is actually a minimum. Good. When you go to 4-speed, same thing. This is the best 4-speed transmission that you can get for that particular configuration. Okay. And how about direct drive? Okay, well, this is direct drive, fuel consumption. So I changed architecture. Okay, now instead of a 2, 3, 4-speed transmission, I go to a single direct drive. Here, it's pretty clear. There is a line, okay, that says below this motor size, I can't do it. I cannot meet the performance requirement. So for sure, the motor will be greater than 360 kilowatts or something like that. But look at what happens. Interestingly enough, there are like 2 minima here, okay? So it's the smallest Pareto front you can have, 2. Okay? Because if it's 1, you don't have to make a decision. If it's 2, you're going to have to say, do I take this or do I take that? Well, from a fuel consumption, the trade-off is, here. I mean, do you pick the smaller number or the larger motor with slightly better fuel consumption? And this is now, so that was the single motor. Now I go to a dual motor, right? Remember that I could take the electric machine and say, let me give you the power in 2 different machines. Well, once again, the combined size also has a pretty clear line. By the way, it's the same as that because in the end you need so much power. Okay, but now there are a variety of different possible configurations that would be optimal in some sense. It's a very steep Pareto front in this case. So you can see the type of study that we do. So let's compare them. I want to show you, I'll start with this plot right here. This is now a different criteria. We're going to consider cost. By the way, notice that I'm jumping from one Pareto front to another because there are many criteria. Now we're going to take a look at cost. And I am going to look at powertrain cost versus freight efficiency. What's freight efficiency? In the world of commercial vehicles, freight efficiency is a very important concept because you could argue that while in a passenger car, 30 miles per gallon is 30 miles per gallon, there's always going to be someone driving the car. A package van, if it has no packages in it, what is freight efficiency? It's exactly 0. Because if I'm not carrying any payload, what the heck am I doing on the road? Those are called, in the industry, they're called empty miles. By the way, sometime in November, I'm going to give a lecture at CAR that is going to be a duplicate of the SAE Buckendale lecture I gave in September, in which I will speak of the commercial vehicle industry and what future technology. We'll advertised, this would be broadly advertised as a car seminar, please come, because some of the comments that I will make there, you will understand well, given this lecture. So freight efficiency is measured in ton miles per gallon. How many miles per gallon I get of fuel economy while carrying so many tons of cargo. If tons is 0, my freight efficiency is 0. So a conventional vehicle has about 40 ton miles per gallon, and its cost is about $15,000. That's your basic Cummins engine with whoever makes the transmission. It could be Allison transmission or Eaton, for example. Okay. With our alternative solutions, I have a cluster up here. So my hybrid vehicle, extended range electric, is going to go from 40 to 140 ton miles per gallon. That's huge. But guess what? Instead of 15 grand, it'll cost me 50 grand to buy this vehicle. We'll come back in a moment to this. Will it be worth it? We'll get there. If I now zoom in on this, I can clearly see what happens. I have direct drive, okay, it's these. Dual motor is that. So dual motor is actually a little better than direct drive. That's, we've learned something. But look at this. The 3-speed and 4-speed transmission are here. The 2-speed transmission solutions are up here. So in this case, it's pretty clear that if what I'm looking at is freight efficiency and cost, remember I have many of these couplings that I can look at. If I look at freight efficiency and cost, it looks like the 2-speed version with a single electric machine and a 2-speed transmission is the best. And in this bottom plot, I threw in an additional criterion, which is also weight. So I have a trade-off. So in my case, the ones that were best from a freight efficiency and cost perspective actually are a little heavier. So you have trade-offs. In the end, when we were finished with this, we found that from a freight efficiency perspective, 2-speed architectures are best. From a motor size perspective, 2-speed architectures are maybe not the smallest motors, but close to it. From a powertrain weight perspective, 2-speed architecture, I said the wrong thing. They were not heavier, they were lighter. So it's actually good for that too. And from a cost, overall cost, it's also very close to the minimum. So the answer that we came up with, after having compared all of these criteria, of the surviving designs that met all the specifications, a 2-speed transmission with an appropriately sized single electric drive is in fact the best answer. And I will close my comments here by saying, so now I have a 15,000 powertrain today, produced every day in Gaffney, South Carolina by Freightliner Custom Chassis with beautiful engines coming from Cummins, okay? That's a $15,000 cost for the powertrain, engine and transmission. I now can say, hey, I can really improve your ton miles per gallon freight efficiency, but it'll cost you $50,000. Now, that's not an insignificant change in cost. Sure, the vehicle overall is much more expensive than $50,000, but that's a significant increase in cost. We've more than tripled the powertrain cost. So how long will it take me to recover this cost? Because if I have better freight efficiency, I'm saving money because I'm using less fuel. Well, the end result is that the crossover point, this is conventional vehicle, and this is the integral of the cost over years of operation. Okay? So the conventional vehicle will cost you this much. Okay? And its beginning cost is the powertrain cost. We start from the starting value of the powertrain cost. When I look at the alternatives, okay, it turns out that the two lines will cross over, and then I will have a favorable slope, shallower slope, so smaller increase at about 3 years. So now it becomes a business decision. The UPS is buying whatever, thousands of these trucks every year. UPS has to make a decision. Will I pay an extra $35,000 per truck, which times many trucks, for every 1,000 trucks is $35 million. So is UPS better off spending $35 million today, knowing that in 3 years they will have made up that money by savings in fuel economy, and from that point on life will look better? Or would they be better off putting $35 million in the bank and getting interest from the $35 million? That is strictly the financial view of things. If you were strictly looking at it that way, the answer is probably UPS would continue running conventional vehicles. You can make more money with cash. But they also understand that there is going to be increasing regulatory pressure to have cleaner vehicles, and I think that these companies understand that they need to do the right thing from a social and environmental perspective as well. So maybe the decision that they will make is, yes, I could make a little bit more money in the market by just investing the dollars, but if I do this, I'm going to have this huge positive image improvement, and also I will already be compliant with future emissions regulations in urban areas. You know, the day may come when in an urban setting you have to be locally zero emissions. In some parts of the world that has already happened. So that is the story I told you today, is how engineering optimization problems that have, as you will see, a fair amount of mathematics in them, how do they match up with real-life requirements? And I think that is an interesting story that hopefully will make you more interested in learning the mathematics of optimization. And so a conclusion of these studies is we look at 5 different architectures. We find out that the 2-speed e-axle stands out, and there are other details of our answer. And recently, I was in China, actually in Weifang, the home of Weichai, Chinese company that makes engines for these types of vehicles as well. And I presented these results there. So this is pretty fresh. I just showed you something that literally I was there in September, okay, just a little more than a month ago. So with that, we close lecture 18, and on Monday, bright and early, come here. The exam will be ready for you, and you will be ready for the exam, right? See you then. Have a great weekend.